Very pleased to have Edgar Bering, who will tell us about ascending chains of free groups in three-manifold.
Thank you, Nathan. Thank you to the organizers for having me. Today, I want to tell you about some work I've done with near Lazarovich. And this is work, well suited for groups around three manifolds, studying ascending chains of free subgroups of three manifold groups. So in the talk, we'll see JSJ decomposition, geometrization. A lot of the things that appeared in Nathan's talk will be tools that we'll put to use. But I want to start by just sort of stating the vague question that motivated all of this. So suppose you're given a group, if it's like any group G, so this is a very vague question, and an ascending chain. I'm going to leave some blanks here. An ascending chain of long blank subgroups. As algebraists, ascending chain conditions have a long tradition in algebra, and so we might ask when, and by that I mean what hypotheses do you need to put on G and H and the chain H? When does this chain HI stabilize? And okay, the vague question is obviously like impossibly too vague. Right? Groups inside groups is too wild. So we might want to restrict our attention to groups we like a lot, or at least groups that I like a lot, restrict our attention to free subgroups. And that's not quite enough to get this question to be sensible. I want to give an example. So if you have a free subgroup, then you have a subgroup that's free of rank 2. And so if G contains the free group on 2 letters, FAB, then G contains this chain of subgroups. A contained in A and A conjugated by B, contained in A conjugated by B, A conjugated by B squared. And this is a proper ascending chain of free subgroups. So it seems like the whole question is just like, when can this stabilize? This is like still a bad question. But this is like a silly example, right? I'm just not doing something useful to build an ascending chain. I found a free group of rank 2, and then there's an infinite ascending chain of unbounded rank in the free group. And so let's add filling in the blank. And this now becomes, when does HI stabilize? And so really, I mean, which groups G have a bounded rank ascending chain condition? So this will be our main question. And the title gives away the theorem. The theorem that I'm going to spend the talk working towards is that three manifold groups are a family of groups for which any chain of bounded rank subgroups stabilize. And so I want to state a careful definition of this property. So definition, a group G has, and I'm stating this definition so I can put the acronym in and then never write out this long 6-word phrase again, has the bounded rank free ascending chain condition, which will be BRACC for the rest of the talk. If every subgroup chain, ascending subgroup chain, bounded rank free subgroups stabilizes. And similarly define constant rank. And these two definitions aren't like usefully different definitions, because the immediate observation is that from the pigeonhole principle, if you have the bounded rank ascending chain condition, then you have the constant rank ascending chain condition, and vice versa. Because if you have a bounded rank chain, interleaved with it is a constant rank chain. And this sort of pigeonhole principle type argument is going to be recurring throughout the talk. And I'm going to get to the point where I sort of gloss over it as a standard technique, but we'll say it carefully now. And so why does free get robbed of the, because I wanted something that I could pronounce, and BRFACC is not a cluster of English consonants that sounds nice. Yeah. Yeah. So what are some BRAC groups? Yeah, that's why free gets robbed of a letter. So examples of BRAC groups to keep in mind. So, I mean, there's the obvious ones like finite groups, finitely generated abelian groups, but there's not so many obvious examples. You can start building groups up out of these. So if you have a short exact sequence, so if you have a finitely generated abelian group, and you've got your quotient here, and this is a BRAC group, then so is G. Okay, these are all like examples that you could give in a graduate group theory class of like, here's a definition, work it out. And a non-example, a group that, you know, is around three manifolds only in the sense that it's excluded, BS12. Right, you can, for those of you who know the group, you can just take your favorite ray stabilizer and then conjugate it a little bit further out the ray. That gives you a proper cyclic subgroup, and then keep going out that ray. So those are some examples and non-examples, but the fun stuff happens when we look at the first interesting example. And this is one that is a three manifold group. And that's free groups themselves, finite rank free groups. Any free group, but I'll only talk about the finite rank ones. This is a theorem originally from a very long time ago, independently due to Takahashi and Higman. I think this is 47 and 49, so very old, maybe 51. Takahashi Higman with a new proof written down by Kapovich and Myasnikov. And their proof is sort of in the tradition of Stallings. And the theorem is a free group of finite rank, so has the bounded rank ascending chain condition. And right, I'm after proving that three manifold groups have the bounded rank ascending chain condition, but all of the key ideas, the motivation, the core goes back to the proof of this fact. And it's beautiful and it's wonderful. Well, the Stallings graph proof. And so I want to give you all that proof in some care, so that you can see how these ideas push forward and connect with hyperbolic geometry. And so to prove a theorem, you always need a lemma. And so I'm going to put the lemma over here because I'll need the lemma again. So I want to record that first I want to just keep up the short exact sequence statement for a long time. And so the lemma is really just a general algebraic lemma about ascending chains of free groups. And it's a free factor avoidance lemma. So suppose H0 subgroup of H1 subgroup ... is an ascending chain of constant rank free groups. Then there exists a chain free subgroups of a fixed ambient group G. Then there exists a chain of subgroups Ki such that two things. First of all, right, when you map a free group into another free group, it could be wild, but this we have some control. So the image, the subgroup Ki plus 1 is not contained in a proper free factor. And the two chains don't exactly interleave, but one is going to stabilize if and only if the other one does. So HI stabilizes only if KI stabilizes. Chain of constant rank free. And this proof, this lemma, it's a nice algebraic exercise. The proof is by induction. If you went into a free factor infinitely often, then take those free factors. That's a new chain. Well, they're proper free factors, so the rank went down. So by induction, either that has a further subchain that has the desired property, or each one of them is missing a free factor. So how do we use this algebraic lemma? Right, there's a name here that should give you a cue for how I'm going to use this algebraic lemma and how we're going to return to the world of topology and make our way to three manifolds. So this is the proof. So without loss of generality, suppose that HI is an ascending chain of free factor avoiding subgroups of Fn of constant rank. So by the lemma, get into the nice case. Well, I want to fix an identification of my finite rank free group as the fundamental group of a graph. Fix that identification once and for all. And now what do? We wonder where our eraser is. Well, I'm going to define the graph gamma I. This is going to be the core subgraph of the cover corresponding to HI, right? This is some finite, each gamma I is finite. And the inclusion, HI including into HI plus 1, induces a map gamma I, an immersion from gamma I to gamma I plus 1. This map is surjective because they're free factor avoiding. Right? If we missed an edge, then the image of HI would be living in a proper free factor. So is onto. So each gamma I plus 1. Oh, wait, right. This map is onto since HI is not in a free factor. But gamma 1 has finitely many edges, and they all have at least n edges. So this stabilizes. So this stabilizes. The cognoscenti might worry about conjugation, but don't worry about conjugation. But this is the core of the argument, is that you get some finiteness and you get this essential immersion. And that essential immersion forces the next step to be smaller unless it's equal. And that's the key idea. And that's the idea that we're going to see as we push this into higher dimensions with more hyperbolic geometry. They can. But they are locally they are isometries. So they're not expanding on edges, because if you look in the universal cover, the minimal subgraph of the action of HI on the universal cover of the ambient graph is a subset of the minimal subgraph for HI plus 1. So yeah, it's not just, right, Dave makes an important point. It's not just that this is an immersion, this is an immersion that is an isometry on edges. So you can't send an edge to a long edge path. Yeah, it's a local isometry. And that's going to come up again later, so keep that in mind. Yeah, so, but this proof in some sense, really didn't use so much about the fact that the ambient group was free as it used the fact that the ambient group acts nicely on a tree in a well-defined way, and you could control things. You could understand the resulting free splittings. And so that brings us to the first generalization of this proof, which is not yet a three-manifold direction, but so we've seen three manifolds have a JSJ decomposition, which splits it up as a nice graph of groups. So the first thing you might want to hope to do is make a similar statement for graphs of groups. So this is the first theorem. So now if you've got a group G, which acts on a tree, G is finitely generated, or sorry, let me state these in a nice order. So suppose G is finitely generated. G acts on a tree T acylindrically. So any path of a bounded length has trivial stabilizer. This is, if you like, no bomb slug solitar allowed. Acylindrically, without inversion, with abelian edge stabilizers, and bounded rank ascending chain condition vertex stabilizers. Or no, sorry, we don't need that. If you've got such an action, if G has a proper bounded rank ascending chain of free subgroups, then it has such a chain that acts elliptically on T. So, okay, I could have stated it as, and the vertex groups have bounded rank ACC, then G has bounded rank ACC. But really, I want you to think of where we're going with this is that T is going to be the Basset tree of a JSJ decomposition. And so if you had a three manifold group which has a bounded rank, which has a ascending chain of free subgroups, suffices to analyze the vertex groups, the pieces of the JSJ decomposition. And the proof is the same. I mean, it's technically more involved, but in spirit, it is the same. So I won't give you all of the details, but I will give you a sketch. So acylindricity plus bounded rank plus the work of Schinitzer, which for those of you who were here, not at this conference, but the previous conference, this came up, Schinitzer and Swarup, on cyclic splittings of free groups. All of this altogether implies that if you have such a chain, is a chain, then the induced splittings, induced minimal splittings, stabilize. Okay, then there is a chain Ki such that the induced minimal splitting stabilize. Wait, no. Yeah, if you have such a chain, then there is a chain such that the graph for the induced minimal splittings stabilize. So in the same way that you can get to be free factor avoiding, with a bit more care, you can be Z factor avoiding, and then the graphs map onto each other, and it becomes a question of vertex groups. There are some technical details involving making sure that you have a reduced thing and making sure that you're actually able to appeal to acylindrical accessibility with care, but I don't want to get into those details because I want to get to the three manifolds in the hyperbolic geometry. But as a nice corollary of this, we recover a result that was proved independently by Schusterman. So fundamental group of a surface has the bounded rank ascending chain condition. And in fact, so our proof, I mean, this splitting fact gets you any cyclic amalgam of free groups in an obvious way. Schusterman used profinite techniques, and I don't really understand Schusterman's proof, so please don't ask me to explain any further than saying that, to prove that actually any limit group has bounded rank ascending chain condition. Completely different proof from our very graph tree action approach. But now I want to change gears and talk about hyperbolic geometry, aiming towards three manifolds. And so I want to give another proof that the fundamental group of a closed surface, sorry, this is a closed surface, that the fundamental group of a closed surface has the bounded rank ascending chain condition, but using hyperbolic geometry. And this is the proof that leads into the world of three manifolds. So let's introduce some hyperbolic geometry. So in the proof that a bounded rank free group has this ascending chain condition, the key finiteness ingredient came from the number of edges in the first cover. And so to make this work in higher dimension, we need something to play that role of the maximum number of edges. And the quantity that's really going to be useful for us is the following. So if you've got a group of hyperbolic isometries that's finitely generated, the total displacement, and okay, I'm looking at isometries in HN, but you could also look at isometries on a tree and write down a similar definition, and you can see the analogy. The total displacement, tau of G, is equal to the nth over all generating sets, finite generating sets, of the nth over all points in hyperbolic in space of, well, the total displacement of this generating set on that test point. And this is going to play the role of number of edges. And this is the quantity that we're going to aim to bound. And why is this a useful thing to bound? Well, it's a fun exercise in using the thick-thin decomposition of a hyperbolic manifold to prove the following lemma. So if M is a finite volume, the finite volume hyperbolic manifold, suppose, given some constant c greater than 0, there are finitely many conjugacy classes of finite subsets of the fundamental group of M with bounded non-zero total displacement. Non-zero is important, you got to avoid the cusps. There are finitely many conjugacy classes of finite set in the fundamental group with total displacement bounded by C. Okay, great. Now we've got some finiteness.
Looks like total displacement is closely related to like the length of a carrier graph.
Yes, it is. And that is a connection that we are hoping to elaborate on that Ian, Nir, and I have been talking about a little bit since last week. But okay, great, this lemma. I told you all not to worry about conjugacy. And for free groups, I think maybe you would believe it, but for subgroups of hyperbolic isometries, maybe you wouldn't.
So this implies that finitely many finite subgroups
Of bounded total, finitely many. So this implies there are finitely many conjugacy classes of non-parabolic subgroup with bounded total displacement. Yeah. And okay, great, there are finitely many conjugacy classes, but maybe you could have some weird conjugacy relation among them. So okay, you can't. This is a theorem due to Huber in n is equal to 2. It has due to Oshika and Voyagailo for n is equal to 3, except to get the statement that as I've written it, you also need the tameness theorem due to Egel and Caligari. Gabai. I don't want to talk about tameness. Those of you who know will know how I'm using it. Those of you who don't, there are plenty of experts here who can tell you how I'm using it. And so for n is equal to 2 or 3, if you have a discrete group of hyperbolic, finitely generated, non-elementary, torsion-free subgroup of hyperbolic isometries, then for all other isometries alpha, for all other isometries, so then for all other isometries, if alpha conjugates G into a subset of itself, then alpha G, alpha inverse is equal to G. So this is how we're going to avoid the conjugacy problem in higher rank. And so, all right, we've got almost all the tools that we need for the surface case. In fact, we have enough tools to start writing the proof. So I'll write the statement. So let sigma be a good compact 2 orbifold. Okay, that's the greatest generality that we can do, but really closed hyperbolic surface. Genus. This is the interesting case that you reduce to. Then the fundamental group of sigma is bounded rank, ascending chain condition. And so for the proof, well, we're going to use that lemma, we're going to use this lemma, we're going to use the theorem. And we're going to use one more tool, which will appear when it's needed. So this is Nirenai's proof. And this proof really motivates the techniques that go into the 3-manifold case. And so this one we'll take a look at. So again, we'll immediately pass to a free factor avoiding chain. So there's a free factor avoiding chain, ascending chain in our fundamental group. Well, for free groups, what do? We passed to the core subgraph and then looked at how they map to each other. Great. Fix a hyperbolic metric on sigma. Then it's nice hyperbolic geometry tells us that let SI be the convex compact core of the cover corresponding to HI. Okay, we have a convex compact core. That's like the core subgraph. Well, right. That's like the core subgraph corresponding to our thing. And so the inclusion, HI as a subgroup of HI plus 1, induces a local isometry. Right? It's not just that it maps edges to edges, it's a local isometry from SI to SI plus 1. And induces a local isometry. And now we use the fact that it's free factor avoiding. since hi is not in a free factor, the image of Si crosses every essential arc of Si plus 1. In the same way that you couldn't miss an edge in the graph case, if there was some essential arc that you missed in the surface setting, well, that arc induces a free splitting, and so you've missed a free factor. Or so you're wound up in a free factor. Yeah, so for n greater than 3, you need to stick in some extra hypotheses about, forget if you need to assume that it's topologically tame or if it's geometrically. You need to make sure that it's tame in the appropriate sense for tameness in a way that I don't have to worry about in dimension 3 because of the tameness theorem. Yes. Yeah, Oshika and Potigailo's paper is for n greater than or equal to 3. The special case for n equals 3 gets a little bit better because of tameness. All right, so we've got our isometric immersions. And they cross every essential arc. So let alpha of Si be the length, the shortest essential arc. And observe alpha of Si is greater than or equal to alpha of S1 for all I, because the shortest essential arc on Si plus 1 crosses Si, so it pulls back to a collection of essential arcs. These are convex cores, so you have a subsegment. And then you can just keep pulling that all the way back. And also the systole, so the shortest closed curve of each Si, well, it's at least the systole of the ambient surface. So there are no super short curves on these SIs because they would be a super short curve on sigma, and sigma has some fixed hyperbolic metric. And so Si as a collection of points inside the moduli space of sigma land in a compact subset. Or sorry, Si definitely don't live in the moduli space of sigma. By the pigeonhole principle, assume all Si are homeo to a fixed surface type S. Great. Now, by Mumford's compactness criterion, the Si are contained in the moduli space of S, but they are in fact contained in a compact subset. Tau is continuous on moduli space. So tau of Si is bounded. And so by the lemma that there are finitely many conjugacy classes of subgroups of Si, plus if they are conjugate into each other, then they're in fact equal, the chain stabilizes. All right, how much time do I have for 3 manifolds? This now is a proof that we can make work for hyperbolic 3 manifolds. And I think we can even make it work in the remaining 12 minutes.
Can you remind us of this principle that you just did?
Yeah, so this is, there are finitely many conjugacy classes. Mumford's compactness condition. So Mumford's compactness condition says that if you look at the moduli space of hyperbolic structures on this surface S, and you look at the subset where the shortest essential arc has positive length and the systole is bounded away from 0, then that subset is a compact subset. And then I have a continuous function on a compact set, so it has a maximum. These aren't compact, or these aren't closed surfaces. Yeah. Yeah, exactly. Yeah. So we have finitely many conjugacy classes. of HI. And so by Uber, we stabilize. Yeah, I'll add that sentence. All right. Three manifolds. I use like every technique I know for three manifolds. All right. M is a closed three manifold. All right, we've had a lot of groups, but they're all around three manifolds. Here we are. M is a closed three manifold. The fundamental group of M has the bounded rank ascending chain condition. And what's the proof? Well, if M has non-trivial JSJ by the combination theorem, by our graph of groups combination theorem. So if a three manifold has a non-trivial JSJ, the corresponding Bass-Serre tree, action of the group on the Bass-Serre tree is acylindrical. And so by the combination theorem, it suffices to handle, well, yeah, it suffices to handle Seifert fiber spaces and a toroidal, which by geometrization, these are hyperbolic. So we've seen several times throughout the mini courses last week and the conference this time, Seifert fiber spaces are handled by the fact that this is why I needed to say the two orbifold case. And if you're worried about some bad fibrations, special cases. Yeah, Seifert fiber spaces are handled by that early example. And so it really becomes something about hyperbolic three manifolds. And since it's before lunch, I think I'm just going to give you the closed case, because I think we're all too hungry to deal with the extra technical mess of parabolics. There might not be lunch. Well, then we definitely are not going to deal with the extra technical mess of parabolics. Oh yeah, that's it's that nervous laughter where you're like, this could go really badly, but I don't want to admit it. Yeah, there might not be. All right. So last theorem. And this theorem works with modification for the finite volume case, but let M be a closed hyperbolic three manifold, then M has bounded rank ascending chain condition. All right, so we use the JSJ decomposition, we use geometrization. What other big tools for understanding three manifolds do I know? The Scott core theorem, Dane's lemma. So they got to make an appearance. Oh yeah, and tameness again. So proof. Let HI, as usual, be our free factor avoiding ascending chain. And so again, by tameness, either HI is a fiber in some finite index cover, or it's quasi-convex. But this is a closed three manifold, so they can't be fibers. So by tameness, HI are all quasi-convex. And the limit set, if the limit sets are all in the same round circle on the boundary, then it's really just the surface case, so we'll avoid that. And they're all quasi-convex. And so the convex hull of the limit set. Yeah, so there's a convex compact core of the cover, Mi. If they're all in some round circle on the boundary, then you can reduce to the surface case and give the surface proof. So discounting that, I can say that in fact all of the convex.
Not saying that it's all contained inside the surface.
Yeah.
Inside the
No. I'm reducing to the surface proof, yeah. Because I want to say that the compact core of the cover Mi corresponding to HI is a hyperbolic handle body. I'm now very conscious of time. Oh, great. plenty of time. And so again, hi going into hi plus 1. Right, I told you there was one idea in the proof. Hi goes into hi plus 1, induces a local isometry from mi into mi plus 1. And we avoid free factors. So the image of mi, so the image, right, why does this compact convex core exist? I'm using the Scott core theorem here. So the image of mi, intersects every compression disk of mi plus 1. So the least area disk alpha area of a compression disk alpha mi plus 1 is at least alpha. Right, and if you think about this in the universal cover, you just have these bigger and bigger convex cores. So of course the disks have to be getting bigger. But right, how are we going to bound? What we really want to bound is the total displacement of these HIs. That's the end game. And so what I want you, so I need a theorem of Epstein and Martin. So the boundary of mi is some pleated surface, but in fact, the boundary of mi is hyperbolic in the induced metric. And so that means that as a hyperbolic surface, the total displacement of hi is bounded above by the total displacement of the fundamental group of the boundary. These are all hyperbolic handle bodies of the same rank, so the boundaries of mi are all homeomorphic hyperbolic surfaces. So they all live in moduli space. All boundary mi live in the moduli space of sigma for sigma closed hyperbolic. And I claim they live in a compact region. And the only tool I haven't used yet is Dane's lemma, so I guess it's time. So if the sequence in mi left a compact, or sorry, boundary mi subset of moduli space, then there exists a sequence of geodesics gamma I contained in the boundary of mi with the length going to 0. Right? That's what it means to leave for a closed surface, what it means to leave the compact part of moduli space. So eventually, gamma is trivial in pi 1 of m. So by Dane's lemma, gamma I bounds an embedded disk. And by convexity, that means gamma I bounds a compression disk for mi. They can't get small. But these have bounded area. Bounded away from 0. So in my final seconds, I'll conclude. Right, this is a contradiction. So the boundaries of mi are in a compact part of the moduli space of sigma. So the total displacement in the chain is bounded. And by our usual end game, it must stabilize. I'll stop there. They do not. So in fact, you can't even save yourself by forcing them to be isometries of hyperbolic 3 space. So Nathan with Caligari gives an example of a free group of rank 6 inside a PSL2C that is conjugate to a proper subgroup of itself via an isometry. And so you can then take the union of all of those, or the ascending H and N, or whatever you like. That's a really sad example. I'm not sure if that one is on the nose hyperbolic, but you can also take your favorite endomorphism of the rank 2 free group that produces a hyperbolic ascending H and N, and that will also be something. Near has a student, if you add the assumption that they're quasi-convex, Near has a student who I think has a mostly finished work in progress saying that yes, for quasi-convex, have like the QC, BRAC, too many letters at that point. Yeah, that seems to be true for hyperbolic groups.
In the argument that's currently on the board, it seems that you're working, quite hard to get into the compact part of the modulus space in the boundary of a handle. And I'm wondering if you can just run the whole argument directly in the, moduli space of hyperbolic three-dimensional structures, like, age of,
Oh,
because it, that also the compact part is like the same.
yeah. So the nice thing about getting into moduli space is that even when there are parabolics, we can handle that setting because we can deal with getting into the compact part of the moduli space of surfaces. And I mean, maybe that also works for the handle body case, but yeah, I don't know. But then we wouldn't get to use Dane's lemma. Yeah.
So another class that has the Takahasi property is the fundamental groups of two complexes with negative emergence. They'll have a sweep proof that's like the graph or surface. You might like it. I don't know.
Yeah. Oh, have you written? Is it written down somewhere, or is it? Okay.
It might be a paper that has it, but otherwise I'll show you.
Yeah. Great.
Any other questions?
Maybe just a word on complement manifold, and that's the word that like for great was not right. In that case,
Sorry.
for composite manifolds.
Yes.
Non-prime.
For non-prime. Oh, right. You use the bigger splitting because our amalgamation theorem was for any graph of groups decomposition with abelian edge stabilizers. So take the combined splitting you get from splitting along spheres and JSJ tori, and that. Yeah. Well, when the moment that you have the free group act on the tree, yeah, virtually abelian is also fine because free subgroup of a virtually abelian group is still Z, which is, that's the key thing, is that the induced splitting of in the amalgamation theorem, the key thing is that the induced splitting of the free group is a cyclic splitting. So yeah, whatever the most general hypothesis you need to ensure that, small. I don't remember off the top of my head. It's very algebraic. The question was, what was Higman's proof of this fact? And it's completely algebraic, and I don't remember it off the top of my head.
If you got fixed rank, you understand take that.
Yes.
It's a low key free group. A low key. The low key free group is free. And the homology is the same rank all the way along. So it can't be an input.
That's Higman's proof.
Oh, is it?
Yeah.
But that would work. It's a low key free group.
Yeah.
But any category is maybe down. If every low key group is free, then it's not really challenging.
Yeah. Yeah. And so actually that's a great thing to bring up. So any locally free group, in a group where every locally free group is free, you can't have such a chain. There are finite volume hyperbolic three manifolds that have locally free subgroups that are not free. So there's something new being done here.
Okay, no further questions. Let's thank Edgar again.